Hello everyone, my name is Palak Jain, Assistant Professor in Department of Computer Science in Arya College Ludhiana. Today, my topic is mealy and Murray machines. First of all, what is finite state machine? That is FSM. A finite state machine is a machine that has many states and has a logical way of changing from one state to another under guiding rules. In this machine, we can change from one state to another. We have so many states in which we can change from one state to another, and that is called transition. So these are the types of FSM, that is finite state machine. We have some machines without output and it answers us in only true or false. But in FSM, we have three types, that is finite state automata, mealy machine, and Murray machine. First of all, that is finite state automata in which it gives output. Second is mealy machine in which it gives us output but it gives output on transition only. Third one is Murray machine and it gives output on state. We will discuss mealy and Murray machine in today's lecture. First of all, what is mealy machine? Basically, mealy machine is an FSM whose output depends on the present state and as well as the present input. So in mealy machine, every transition for the particular input symbol has a fixed output. So as mealy machine has six tuples, as you can see in this picture, there are six tuples for the mealy machine, that is Q, which represents the finite states, that is finite set of states, that is how many states we require in our machine. So second is that is summation symbol and it is used for finite set of symbols that is called the input alphabet. Then third one is O, which is a finite set of symbols that is called output alphabet, right? Then we have this symbol that is delta, which is the input transition function, as we can say that if we transit or if we change from one state to another state through any input, then it is called the transition function. Then we have that is X, which is the output transition function, in which as if we are in suppose we are in A state, then it gives some output, so it is the transition function which is X. Then we have Q naught, which is the initial state from where any input is processed. We can take Q naught or we can take some other alphabets also, but in general form we can represent it as a Q naught. Then we have the state diagram of mealy machine. As you can see in this diagram, that is in mealy machine, as I have already told you that every input has one output. So you can see in this figure that is there are four states which represents in green color. We can take it as Q0, Q1, Q2 and Q3 or some other symbols. So in this, if we get 0, then slash 1, first symbol that is 0, in all these we have seen that 0 or 1, this is the input symbol which we have seen in the first place, which is the input symbol, and slash, then second symbol which we can see in this picture is that is output. So in if we see that in the first circle, that is green, that is suppose we can say it is Q naught state, that is the initial state. In this, if we get 0 input, then we get 1 as an output. So basically this is the diagram of mealy machine in which every input has one of its output. So mealy machine basically it gives us the output value and its output value depends upon the present state and the current input symbol. So this is the mealy transition table. Suppose this is not linked with the previous picture, but as we have discussed this in previous picture, that we have discussed the state diagram, and second method is we can represent the mealy machine in the transition table, as you can see in this picture. So we can represent the transition table as follows, in which we have Q0, Q1, Q2, Q3. These are the present states. For example, as we can see that the in Q0, right, in where we can place the Q0, we see the symbol that is arrow before the Q0, which represent it is the starting symbol, right? So we have four states: Q0, Q1, Q2, and Q3. So with respect to every present state, we get another state when we get an input. For example, if we see in this picture, if we are at the starting position, that is at Q naught, if we get zero input, then we reached at the Q3 state with output 0. Similarly, if we at Q1 state, then if we get 0, it reached at Q naught with output 1. Similarly, Q2 and Q3 are the same respectively, right? So we have in this transition table, we see that there are two input symbols, that is 0 and 1, and the output is also 0 and 1. So with respect to every state, when some input is passed through state, we reach to another state with some output, right? Now we have the another machine, that is Murray machine. So in Murray machine also, the output function that depends on the present state only, and the Murray machine is described by the six tuples, as we have already discussed in mealy machines. So it is almost same, but few differences are there. So first of all, Q, that is finite non-empty set of states. Then summation symbol, that is set of input alphabets. Then we have set of output alphabets. Then the transition function, right? Then we have output function. And last but not the least, that is the Q naught, which is the initial state, right? Then the transition table for the Murray machine is, there is no concept of final state in Murray machines. So we consider the output for each state. In mealy machine, we consider the output with every input symbol, but in Murray machine, we consider the output for every state. Like for example, in this transition table, we have four present states, that is Q0, Q1, Q2, Q3, in which Q0 is the initial state. So when we are at Q0, if we get 0 as an input, then it reached at Q3 state, right? Then if we get 1 as an input, then we reached at Q1. Similarly with Q1, Q2 and Q3, we reached at different states when we get 0 as well as the 1 input. So in this Murray transition table, we can see that in Murray machine, the output is associated or output is considered with each state. For in this table, we can see that output is 1 0 0 1. For Q0, we have output 1. For Q1, we have output 0, Q2 0, and Q3 1. These are the output with present states. We can see this in our next um, slide, that is state diagram of Murray machine, in which we can see that there are four states with which every input is associated, right? Like we have S0, S1, S2, and S3. There are four states. So with each state we have one output. That is, with S0 we have 1 as an output, S1 0 as an output, S2 0 as an output, and S3 1 as an output. So 0 and 1, as we can see with the arrows, these are the inputs that we have to give. For example, if we see that in this picture, if we are at the S0 state, we get, if we get 0 as an input, then we get, we reached at S0, same state, but the output is 1. If we are at S0 and we get a 1 as an input, then we reached at S1 and our input symbol is 1, right? So in this Moore machine, every input is given and the output is associated with each state, right? Then we now will convert the Moore machine to mealy machine, as input is Moore machine and we get mealy machine basically, right? So there are three steps for this to convert the Moore machine to mealy machine. First of all, first step is take a blank mealy machine transition table format. Step 2, we have to copy all the Moore machine transition states into the table format of mealy machine, right? Then we have step 3. In it, we check the present state and their corresponding outputs in the Moore machines. Then for a state Qi, output is M, copy it into the output columns of the mealy machine state table wherever Qi appears in the next state. So let us take an example. This is an example. For example, we consider this Moore table, right? In it, we have four present states A, B, C, and D. And if we are at the present state A, then if we get 0 as an input, then we reached at D, and 1 as an input, we reached B. Similarly with the B, C, and D states, right? So in as we have discussed that in Moore machine, every state is associated with one output. So if we are at the present state A, its output is 1, B 0, C 0, and D 1. These are the output that are associated with the states, right? If we want to convert it into the mealy machine, then first of all, these are the step 1 and 2 as we have read, that we have to make a table that is similarly as we have seen in this Moore table. Present states ABCD, that is present state ABCD. Okay. Then we have states where we reached, like when we get 0 and when we get 1, as you can see in this picture. But in this, we have shown different output columns for every input, because in the as we have seen in the Moore table, the output is associated with the states, but in the mealy machine, output is associated with the input symbol, right? So every input we get an output, right? So we write output as follows, as we have seen in the first table, this one. A has output 1, B has 0, C has 0, and D has 1. Now see in this A, when we reach at D, D's output is 1. B, when we reached at A, output is 1. C, when we reach at C, output is 0. And D, when we reach at B, output is 0. So in this, we make the table as same as that of the Moore, but the difference is that every output is associated with the input symbol, right? So we convert the Moore machine to mealy machine. This is simple. Now, second one is if we convert the mealy machine to Moore machine. In this, input is mealy machine and output is Moore machine, right? There are three steps in this. First step is calculate the number of different outputs for each state that are available in the state table of the mealy machine. Second step is if all the outputs of the Qi are same, then copy state Qi. If it has n distinct outputs, then break the Qi into n states. Then step 3, if the output of the initial state is 1, then insert a new initial state at the beginning which gives 0 output. Let us take an example. This is an example. So we consider the mealy machine. As you can see, A, B, C, D, and we have inputs 0 and 1, and then we have outputs. Here we can see that A and D, it gives only 1 and 0 outputs respectively, right? So we retain the A and D. But when we see at states B and C, it gives different outputs, that is 1 and 0. As you can see that when we are at the B state, it we have 0 as an input, then we reached at A and we get output 1, right? So when we same if we consider the same symbol, that is for the C, we get 0 as an input and we reached at C and we get output 1, right? Similarly, we can see in the B state, that is when we get 1, we reached at D, we get 0, right? In the C, we get 1, then we are at C state, but we get output 0, right? When we are at the C state, when we get an input 0, it is at the output 1, but when we get the 1 as an input, then we are at the output 0. So B and C produces the different outputs 1 and 0. So we divide B into B0 and B1 and C into C0 and C1. So this is the conversion in which the present state A and D remain same, but we divide the B and C into B0 and B1, C0 and C1 because of the input 0, because of the output 0 and 1. Similarly, with this, we get the output results as follows, as you can see in this picture, right? So we can easily convert this transition table. Now we have the difference between the mealy and the Murray machines. So the mealy machine, that output depends upon the present state and present output, but in the Murray machine, output depends only upon the present state. Second, generally in the mealy machine, it has fewer states than the Murray machine, but in the Murray machine, it has more states than the mealy machine. In mealy machine, output changes at the clock edges, but in the Murray machines, input change can cause change in the output change as soon as the logic is done. In mealy machines, it reacts faster to inputs, but in the Murray, it do not react more, we can say that the more faster as compared to the melee. So more logic is needed to decode the output since it has more circuit delays, right? As we can see, as we have already seen in examples, right? So these are the advantages of melee and the Murray state machines. As the Murray machines are cheap, they are easy to use. So Murray state machines are very fast. Melee machines are reactive, that is they have the low response time, that is they are very fast. These are the disadvantages of melee and the Murray state machines. Melee state machines are expensive to produce and number of states can become unmanageable as there are too many states sometimes. So, so these are the uses of melee and the Murray state machines, as melee state machines are used in the processors due to the property of having many states, and in these machines they are also used to provide a rudimentary mathematical model for the cipher machines. And in the Murray machines, it is used as a write enable in the SRAM because of its speed. It is used in SRAM because SRAM needs a level sensitive control. It has a signal that has to be asserted for an amount of time. Then we conclude our today's topic with mealy and the Murray state machines. They are very important concepts in the digital design, and these machines can be used in the design of mathematical algorithms also. And these machines can come in both simple, that is having the one input and one output, as well as in the complex form, that is having the many inputs and many output types. I hope you understand very well about the mealy and the Murray machines. Thank you very much.